Hello, this is a brief tutorial of how to perform tests for differences between 3 or more independent groups of data. And the data set that we will use for this purpose is quite simple. The number of seconds that it took different dogs to perform an experiment to solve a puzzle. And we are looking at differences in that time that it took them to solve the puzzle in 3 different breeds. So I will just quickly go into our variable view. And what we have is seconds, so seconds that it took each of those dogs to solve the puzzle, which is a continuous variable as it has a unit, and that is in SPSS defined as scale. And then we have breed, which takes the form of 3 different variants. The first one being Chihuahua, the second one being Springer Spaniel, and the third one being Labrador. Okay, so I have defined this previously, and that makes it a nominal variable. So going back into our data view, in order to find out whether it took one of these breeds longer or shorter to solve this puzzle, we first need to perform a test for normality, because there are 2 different tests that will give us an answer of whether there is a difference between the dog breeds. One of them is parametric and one of them is non-parametric. Now the parametric version is called an analysis of variance, or ANOVA, and the non-parametric version is called a Kroskal-Wallis test. And whether or not we can use the parametric ANOVA depends on whether the data are normally distributed. So whether they're in this data here, the seconds to solve the puzzle, there are any significant outliers or not. Now, in order to perform this test for normality, that will tell us which test for differences to use. We go into Analyze, Descriptive Statistics, and Explore. And we need to move our dependent variable, the one we've measured, into the dependent list, which is over here. And then we need to select in the plots option the normality plots with tests, which give us our normality tests. We deselect everything else because we don't need that at the moment, and we just select plots down here so we don't get all the other gumph as well, and then click OK. And this is our result. So these are the 2 tests that have performed a test for normality. One of them is called a Kolmogorov-Smirnov test, the other one the Shapiro-Wilk. They essentially do the same thing, but one of them is considered more reliable, especially when you have small sample sizes. Now in this case they both agree because their p-values are both over 0.05, which we consider as non-significant, and that tells us that we accept the null hypothesis in this case, that our data are not different from a normal distribution. Okay, so the data are normally distributed. There are no significant outliers in this data, so we can use a parametric test to look for differences between the seconds it took the dogs to solve the puzzle between the different dog breeds. Okay, so in order to perform this test, which as I mentioned is called an analysis of variance, or ANOVA, we go back into Analyze, Compare Means, because in the parametric tests that we use, it is the average or the mean that is used to compare the measurements between the different groups. Okay, and we go down to one-way ANOVA. The one-way ANOVA is one way because we only input one independent variable. Now, ANOVAs can handle more than one, but that is the matter for another tutorial. So in our dependent list, we need the dependent variable, so the one we've measured. And in our factor list, we need our dog breed, which is our independent variable. We hit OK. Now, one of the things that an ANOVA does is, or what the ANOVA does is generally tell us whether there is a difference in this data. So generally between any of these 3 groups, are any of them different from any others? And it will return a significant result if only one of those groups is different from the 2 others. What it does not tell us is which groups are different from which others. Okay, so it only tells us whether overall there is a difference or a significant effect of dog breed on the seconds it took these dogs to solve a puzzle. In order to get a more detailed result to find out whether whether the difference lies between the Chihuahuas and the Springer Spaniels, or the Chihuahuas and the Labradors, or maybe the Springer Spaniels and the Labradors, we need to perform what is called a post hoc analysis. Now this option is right here, and I will select this now before I run my ANOVA, so I basically get both results in one go. And there are loads of different options here. All they are is essentially just different versions of the same thing. I will select the Tukey here, and that is simply a matter of opinion with different people use different tests. The other one you could be using is the Bonferroni here, which is more conservative, so it's less likely to return a significant p-value. The Tukey test is generally used for small sample sizes, so it's what I will be using here. So I will click continue, and then we will look at our results by clicking OK now. Okay, so the first thing that this returns is the result of the ANOVA. That's the analysis of variance that tells us generally, is there a difference between the groups in terms of seconds that it took them to solve the puzzle. Okay, and the most important value here is this one right here, the significance value or p-value, and that in this case is less than 0.05, which means that we reject the null hypothesis that there is no difference between the groups. So actually, yes, there is. Okay, at least one of these groups has solved the puzzle quicker than the two others. Now, in order to find out which groups are different, we go into our multiple comparisons. Now, you may wonder why it is necessary to look at the overall difference first and then go into the multiple comparisons. Now, the reasons for that is that if we do multiple comparisons straight away and we just compare each of the groups to one of the others, so that until we have all the combinations, we are running into the likelihood, or we run the danger of getting a p-value which is not true. So it's both of the options are possible, that either we get a p-value which says that there is a difference and actually there isn't, and also the option that we get a p-value that says there is no difference but actually there is. That likelihood of those two things happening is increased the more often we compare the same thing. So we basically get an idea of whether there is a difference overall first, and then we look into the specific differences later on in the multiple comparisons. Now this is our Tukey test that we selected, and essentially what it does is it lists each of the dog breeds here, and then it compares them to each of the others. Okay, so in this row right here we have the comparison between Chihuahua and Springer Spaniel, and in this row here we have the comparison between Labrador and Chihuahua. Okay, and in the first comparison, Chihuahua, Springer Spaniel, significance value, the p-value right here, is less than 0.05. So there is a difference in the seconds that it took the Chihuahua to solve this puzzle and the seconds that it took the Springer Spaniel to solve the puzzle. Okay, there is also a significant difference between the time it took the Chihuahua to solve the puzzle and the time it took the Labradors to solve the puzzle, which is this p-value here, which is also significant. Okay, we then compare the Springer Spaniel to both the others. Now we already know this result because we've seen it up here, so that's where the p-value is the same. However, here we have the Springer Spaniel versus the Labrador, and actually there was no difference between those two. Okay, so essentially this is what that multiple comparisons function does, and now we know that there is actually a significant difference between the time it takes the different animals to solve the puzzles, and that is the Chihuahua, which is different from both of the others, whereas there's no difference between Springer Spaniels and Labradors in how long it takes them to solve the puzzle. So now, in order to find out what direction this is in, we would need to perform some descriptive statistics. Okay, so we would essentially need to look at the actual averages of how long it took them to solve the puzzle. We can also just look at our data a little bit and see that generally these Chihuahuas were a bit quicker than the rest. Okay, so in order to get a proper idea of this, we would need to perform, we'd need to create a graph, which is the content of a different video. In this case, it would be a bar chart with error bars. Now, to look at the situation of having a non-parametric data set, which does not follow the normal distribution and has actually got some outliers, we will just insert an outlier here. So let's say this Springer Spaniel right here, while they were solving the puzzle, they got distracted by something, and they took a lot longer to solve the puzzle than the rest of the dogs. Okay, so I'll change this value here to a very high one. And we will see what this does to our test for normality. So I'm going to run this again. Okay, same that I did before, and I have my plots option here selected for the normality tests. And the output now is different from before. Now before we had both of these tests with a p-value of over 0.05, which shows us that the data are no different from normal. Now in this case, the Shapiro-Wilk, which is the one we usually find more reliable, has a significant value or a p-value of less than 0.05. And that means that there is a difference between this data, the seconds it took the dogs to solve the puzzle, and a normal distribution. So these data are now no longer normally distributed because of this outlier that I have introduced. So now we need to perform the non-parametric version of the test for differences between the three groups. And that is called a Kruskal-Wallis test. We find this in Analyze, Non-Parametric Tests, Legacy Dialogues, and then K, Independent Samples. Okay. Now the test variable in this case, that's the dependent variable, so the one we've measured, seconds to perform and solve the puzzle. And the grouping variable is dog breed. Now we need to quickly define the range here, which is just simply saying what is the smallest category value, which is 1, and what is the largest category value, which is 3. So we're just telling SPSS that we have 3 different categories. Kruskal-Wallis is already selected, that is the test that we have to perform, and then we click OK. And what we get is this result here, and it tells us just like the ANOVA did before, but using ranks, and actually, which means using medians and the dispersions that go with the median rather than the averages to look at differences in the seconds it took the dogs to solve the puzzle between the groups. And the result is a p-value which is less than 0.05. So yes, there is a difference between the time it took these dogs to solve the puzzle, just as before. Now, the Kruskal-Wallis test or the non-parametric tests do not have an automatic post hoc analysis option, which would give us the information of which groups specifically are different from each other. Is it the Chihuahua? Is it the Springer Spaniel? Is it the Labrador? Are they all different, or is it just one of them? So in order to know this, when we've done a Kruskal-Wallis test, we actually need to perform separate Mann-Whitney U tests between the different groups. Okay. Now, the Mann-Whitney U test is also covered in another video, which is the one for independent samples between 2 groups. But what we can do here, in order to just show you how that would be done, is to perform one of them. So the Mann-Whitney U test is in, again, Analyze, Non-Parametric Tests, Legacy Dialogues, but then we just go to 2 independent samples rather than K. Okay. And again, we have our test variable, which is the dependent. We have our grouping variable, which is dog breed. Now, when we define the groups here, we basically can select the different combinations of the groups. So we can first compare group 1, which is Chihuahua, to group 2, which is Springer Spaniel, and then run the test on this. And then in the next, we basically look at the result of this, and then we do the same thing again, but then we replace, say, 2 with 3. So now we're comparing Chihuahua with Labrador. And then in the last combination, we need to compare Springer Spaniel and Labrador. Okay, so for now, we'll just compare the groups 1 and 2. So that's Chihuahua and Springer Spaniel. Mann-Whitney is already selected, and I click OK. And then this is my result. And as before, we get the p-value, and we look at this one right here, the asymptotic p-value, which is for a two-tailed test. And it shows us, again, a p-value of less than 0.05, which we had before in the ANOVA, because we found before already that there is a significant difference between the Chihuahua and both of the other groups. Now, if you repeat this for the other combinations, you'll find the same thing. Chihuahuas are different to both others, but there's no difference between the Labradors and the Springer Spaniels. Okay, so a very quick tutorial of how to perform these tests for differences between 3 or more groups.